Hey, what's Sheldon supposed to be?
Oh, he's the Doppler effect.
Yes. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Oh, sure, I see it now, the Doppler Effect. All right, I got it.
Well, hello guys, Mr. G here, and we are going to be making another video for the grade 12. Today we're going to be talking about Doppler effect, which is the next topic after work, and we're going to be making a short video with the most important thing you need to know about Doppler effect, the formula, how to understand the formula, and that is what is going to be today. Before we carry on, please subscribe for the channel so you can get all the notifications and a post I do on a daily basis. So we want to start with the Doppler effect, and we're going to go straight to the definition, guys. This is a long definition. It's not that difficult, but it's a little bit too long, and then we're going to explain what is going on there. Now, Doppler effect states that is the change in frequency of sound. Remember, we're going to work also with light. Is the change in frequency of sound detected by the listener. So in this case, we are going to have something called the listener or the detector, because the sound source and the listener have different velocities relative to the medium of sound propagation. This is the Doppler effect. Is going to be in the exam for sure. It is always going to be there. Now, the formula is also going to be in the exam. What is the formula for Doppler effect? And I'm going to be reading this one. Frequency of the listener is going to be equal to speed of sound in the medium that we are working with, whatever medium, could be water, could be air, could be any other medium, plus minus the speed at which the listener is moving divided by the speed of sound plus minus the speed of the source, multiply everything by the frequency of the source. And this is the formula for Doppler effect. So now here we having a source and we having the listener. So we having a source and we having a listener, and we have to remember that one is important. S is for source, L is for listener or detector. This is the formula, and now we're going to be looking at all the possible ways how this can be a thing. Okay, guys, this is the first scenario we are going to be looking at. We have in a source here on the left side, which is a siren, and we have a person on the right side, which is going to be the listener. Neither of them is moving, and let's see, this siren is producing sound of certain frequency. And if we represent sound like this, more or less this is what is happening there. All of them are evenly, and the person will receive the same frequency as the source. So in this case, the listener is going to detect sounds with the same frequency as the ones emitted by the source. That is happen when the two ones are at rest. Neither of them are moving. Now let's go to change, and then let's keep the source in this case at rest, but the person is going to start moving. Now let's see what happened here. The siren is at rest, it's not moving, but the listener is moving towards the siren. So now you have to remember that this wave is moving, or the frequency of this wave are moving in that direction. Right? Now, as one of them move a little bit further to the front, so that the man is going to move to the left. So it will get the next frequency faster than it would be if it's at rest. So that is what is happening. So the frequency detected by this person is going to be higher because it's moving in the opposite direction of the wave. So when the person is already here, the other wave, it will be also moving to the front. So the other wave will be already. We can conclude that the frequency detected is going to be higher than the actual frequency produced by the siren, because the person is moving towards. And therefore, the speed of wave relative to the listener will be the addition v of sound plus the v of the speed of the listener. I'm going to just write the L because it was in the formula. If it's moving toward, what is going to happen is this one, because they moving, so you add the velocities here. So if you go to the general formula, we are talking about the one on top here, this side here on top, and then it's going to be a plus. So the final formula will be like this one. So this is what happened when the listener is moving toward. This is the final formula, because at the bottom, then the speed of the source is 0. It's not moving. So this is the second scenario. Let's go to the third scenario. Now, in the third scenario, what is going to happen? We are going to keep the siren or source at rest, but we are going to move, the person is going to be moving away from the source. So what is going to happen here, guys? For instance, the person will take longer to reach this wave, as well as this wave will take longer to reach him. So the frequency detected by the person will be less than the frequency produced by the source. So if the person is moving away, the frequency detected is going to be less than the actual frequency produced by the source. And in the formula, in this case, you're going to say that v of the speed of sound minus the speed of the listener. And in the formula, then you will have that in this case, the one top is minus. You can see in the second scenario was plus, that is when the listener is moving towards and the source is at rest. This one is when the listener moving away and the source is at rest. Let's go to scenario 4. There's only 4 scenarios we're going to look at. Now, in this scenario, what is going to be moving is, the siren, but the person or the listener, whatever is the listener, it doesn't need to be a person, it could be a bird, is going to be at rest. So what is going to happen, because the siren is moving in that direction, so what is going to happen is that it's going to compress the wavelength or the wave. The waves are going to become shorter in length because it is moving and then producing the next one and it's moving. So it's like compressing and compressing like a spring. That is what is happening here. Okay, note, because of that shortening the length of the wavelength of the wave, this person will detect a wave with a higher frequency. So the frequency detected by this person is higher because the siren is now compressing the waves. So in this case here, the frequency detected is also higher than the frequency of the source. The source is moving toward, is compressing the wave, so the wavelength of this wave is shorter, but due to that fact, the frequency detected by the person is then higher. So in this case, we're going to say that the speed of sound is going to be minus the speed of the source. That is the other scenario. When you write the formula here, then the formula will be frequency of the listener equal to speed of sound plus minus speed of listener, but that one is 0 because the person or listener is not moving, and then at the bottom is speed of sound minus speed of source. Let's write the V. And everything multiplied by the frequency of the source. This is the other scenario. Note here at the bottom we're using a minus. And the very final scenario we're going to see. So in this last scenario, what is going to happen is that the siren is going to be moving away. And as the siren move away, what is going to happen is going to be a longer wavelength. It's going to now pull this wave away like if it was a spring, so the wave will become then longer. Like for example, it's moving and then it's moving, then it's produce another one, and the length of the wavelength of the wave become longer, and therefore because of that, the frequency detected by this person will be less. So in this case, the frequency detected is also going to be less than the frequency produced by the source, because of the source is now making the wavelengths longer. And in this case, you are going to say that E is going to be V of sound plus the V of speed of the source. And then in the formula, in the complete general formula, is going to be frequency of listener. On top is V of sound. V of listener is 0 because the listener is not moving, divided by V of sound plus the V of the source. Everything multiplied by the frequency of the source. In this case, then it's like this. So as you can see here, we have all the possible scenarios. Starting, I count 4 scenarios because the first one is when neither of them is moving. Obviously, it's going to be the same. But the second scenario, when the person is moving toward, then here is the formula you have to use, is this one in this specific way. When the person is moving away, the same formula, but you are going to use it in this way. That is what I'm saying. And then scenario 4 is when the source is moving toward, then you are going to do it like this. And the final scenario is when the siren of the source is moving away, and this is the formula. So note the following. This one here is the general formula, and important is that in the exams, if you don't write it in this way, you lose the mark. That is a very important detail. So you have to write it in that way, in which there is the plus minus at the bottom and there is a plus minus at the bottom, and then according to the scenario, then you are going to use this different way of solving it, if it's positive top or minus top or so on. So this is how you apply the formula, guys. And then we can do a quickly example here of calculations. All right, and here is the example. A man is standing on a pavement. A man is not moving. When he hears an ambulance approaching, the ambulance is approaching. This is an important thing. The source is moving towards. So if we go here, it will be this scenario here where the source is moving toward. This is quite simple. The siren is emitting wave with frequencies of 500 Hz. So that 500 is the frequency of the source, or produced by the source, and it is equal to 500 Hz. The ambulance moves at constant speed. The speed of the source of the ambulance is equal to 30 meters per second, and it's moving at constant speed. Calculate the frequency detected by the man. So the frequency of the listener, this is the question mark. The speed of the sound in A is equal to 340 meters per second, and then we have that the speed of the listener is equal to 0 because it is not moving. So now, guys, important, you are going to write the formula as it is given to you in the exam, as for instance, V of sound plus minus V of the listener divided by V of sound plus minus the V of the source multiplied by the frequency of the source. You always are going to write the formula in this way, and it's very easy because that formula is given to you. Now then you are going to come to the scenario. In this case, we said that the source is moving towards, so this is the scenario, and we are going to take this formula as it is here to the question that we are busy with. So I took it, and we are going to place that formula here in that specific way. There is the formula. So this is the scenario. This is what we do. Now the rest is just substituting. So now you substitute everything you have, and it's going to be like this. Then the answer is 550 Hz. This is just a simple example. The questions could be a little bit more tricky than this, but this is all for now. So this is Doppler effect. This is Doppler effect for sound. Still we have to speak something about Doppler effect for light, but no, it's not going to be in this video. Next time we'll go about Doppler effect for light. It is very useful. We use this one in medicine all the time when they do a Doppler and they use lights and colors for that. And then thank you for watching, guys. If you think it helped, please subscribe for the channel so you can get all the notifications, the worksheet, and all the videos. I'll see you next time. Mr. G here.
Hi.
Hi. Hello.
So what are you supposed to be?
Me? I'll give you a hint. Meow.
Choo-choo train?
Close. Meow.
A brain damaged choo-choo train?